Hello, we are wrapping up week 4 of laser research. So most of what we've been doing this week is to attend and give some presentations. This is a pretty common thing when you're working in a research lab. You're going to have to see other people, present about their work, which is pretty cool, and also present about the work that you're doing. So Susan and I spent a lot of time preparing for our presentation, and we gave our presentation. We had some fun with it because we didn't just talk about stuff that was going on in the lab, since we were talking to a research group that they all already know what happens in the lab. So we spent a lot of time talking also about what we do as teachers, and I think that was something that was interesting to them, because then they get to find out what are we taking back to our classroom. How are the high school students benefiting from the fact that we're here? So that's a lot of what we've been doing this week. As far as work in the lab goes, it's been a lot of realigning this fiber, and I want to tell you a little bit about the fiber. I think I've shown it before, but it's this long, thin optical piece, and what we do is we pump it down to vacuum, and then we fill it up with argon. And when our laser beam passes through it, the gas is going to cause the beam to have a wider bandwidth. That is to say, there will be a wider range of frequencies that are transmitted from the fiber. So when we get the beam on the outside, maybe when it came in it looked kind of red, but when it comes out it's going to look a little more white, because when you have a lot of different colors mixed together, that makes it look white. The cool thing about having that wider range of frequencies is that lets you get a shorter pulse in the end. If you've been keeping up with my Quantum Basically series, then you've learned something about Heisenberg's uncertainty principle. Heisenberg's uncertainty principle means a couple of different things. It means that you can't precisely know where a particle is and how fast it's going, but it means something else. It also means that there's a limit to how narrow the bandwidth of a pulse can be and how long it can last. So the narrower that bandwidth is, the longer the pulse has to be, and the wider that bandwidth is, the shorter the pulse has to be. The bandwidth being how many frequencies are present in the pulse itself. So when we send the light through this fiber, that spreads out the bandwidth so that you can get a shorter pulse in the end, which is really what we're going for. I also realized I probably never talked about why it's really important to have short pulses. Having short pulses is like having a fast shutter speed on a camera. The more flashes you're able to get per period of time, this is on a video camera or something like that, the better resolution and the better frame rate you're gonna get. When you're dealing with really, really fast processes, like molecular processes, you're gonna need a very, very fast shutter speed to be able to kind of take a video of what's going on, and that's what we're doing by making these really short pulses. But right now, a lot of what we're doing is optical alignment, and that's pretty typical for an optics lab. We've got 2 weeks left, so stay tuned. I will see you again next Saturday.